Question 2. This question is to investigate the effects of temperature on the equilibrium constant K1 between these species, iron 3, thiocyanate, and iron thiocyanate. Okay, to set up this equilibrium, aqueous iron 3 nitrate is mixed with the aqueous potassium thiocyanate, and the products, the iron thiocyanate ions, is red color. So therefore, we use the calorimeter to measure the absorbance of the reaction mixture, and a calibration graph then used to determine the concentration of this iron thiocyanate. Okay, first let's discuss about how the calorimeter works for this experiment. Okay, first, this one is the calorimeter that we used, and inside this meter it has a light source, so we can select a particular wavelength pass through the sample. The sample, of course, it must be color, and it will absorb certain wavelength. Once the light being transmitted, the detectors will tell us how much of this light being absorbed by showing the absorbance. Higher absorbance means more light being absorbed, means the solution is color is more intense, is absorbed the more wavelength. Again, when the absorbance is higher, means the color of the solution is more intense. It can absorb more wavelength. Okay, so now table 2.1 shows the solutions for the experiment. So we have 4 solutions, A, B, C, D. So the first 2 is the thiocyanate. So it's 0.0092 and 0.02. After that, for the C and D is iron 3 solution. So it's 0.02 and 0.5. Okay, later we will discuss about the absorbance. Okay, let's start with the preparation of the solution. Describe how you would prepare 100 cm³ of the solution B from solution A. Solution B and A again is a thiocyanate solution. The A is more concentrated, B is a diluted solution. So before you start the steps or explanation, you must know the volumes of A that will be taken. So when we do a dilution, we must take a solutions which is more concentrated and dilute it. So how much we going to take from this solution A? So we must use the M1V1 equal to M2V2 to get this volume. Okay, let's say M1 is the concentration for the solution A. V1 is the volumes that we need to take from solution A. M2 is the concentration that we need to prepare, 0.002 in this case. V2 is already mentioned, 100 cm³. So by doing this, we know that the V1 means the volume from the solution A is 21.74 cm³. Okay, but in the steps later, you cannot put 21.74. Why? Because when we want to take a volume, let's say from burette uncertainties only to 0.05 plus minus 0.05 cm³. So means we cannot really take exactly 21.74 cm³ from the burette. Because in the lab, one of the most accurate apparatus that we can take solution is a burette. So therefore, you must put, it's not better, you must put 21.75 cm cube. You cannot put 21.74 cm cube. Okay, so now, this is the first step. Take 21.75 cm cube from solution A using burette and transfer the solution to the 100 cm cube volumetric flask. So you must put volumetric flask. For a dilution, we always need to use the VF. After we transfer 21.75 cm cube of solution A into the VF, then we need to top up the flask, and it must top up to the calibration mark. Normally in the VF there will be one mark here, so you need to add water until it's reached this calibration mark. After that, another one that you need to be careful is, after top up, means during the top up we need to use the distilled water. So distilled water must be there, cannot simply just mention water, must use distilled water. Okay, once it's reached the calibration mark, we need to put the stopper, invert shake the flask, which to homogenize the solution. Okay, these are the steps that you must give. Part B. Before starting the experiment, solution B and D are used to produce calibration graph. Calibration graph is something like this, right? To show a certain absorbance with the concentration. After that, Nernst volume of each solution are added together, and the absorbance of each mixture is recorded. Okay, so we get this the calibration graph just now. The concentration of solution D is much greater than the concentration of B. From this table you should know the D is 0.5, B is only 0.002. This is much greater, right? So why we want to do that? Okay, because this one is again this is D, this is B. So because we want to make sure the concentration of the iron thiocyanate is all from the thiocyanate from solution B, means the concentration of the products, it will be from this one, because this one is in excess. So whenever it's formed, means the iron thiocyanate, it must from this thiocyanate. Okay, that's the purpose. Okay, later we get back to this calibration graph. Okay, part C. The following experiment procedure is used. Okay, step 1. Half fill a large beaker with water at room temperature. Transfer 40 cm cube of solution B into a boiling tube. Place in the boiling tube in the beaker of water. After that, transfer 5 cm cube of solution C, okay, which is iron 3 now, into the test tube and place the test tube in the beaker of water. Means now the beaker has the boiling tube and the test tube, right? And the temperature is 25 degrees C. Wait for 10 minutes. Okay, why we want to wait for 10 minutes? We want the mixture that inside the boiling tube and test tube reach the thermal equilibrium, okay, with the water bath, means the same temperature as water bath. Okay, step 5. Transfer 5 cm cube of this solution B from the boiling tube to the test tube that containing C. Stir the mixture in the test tube and record the temperatures of the mixture. Okay, during this step, the color already produced. When the solution B added to this solution C, so the red color produced. After that, we measure the absorbance of the mixture in the test tube using the calorimeter. Okay, change the temperature of the water in the pickle and repeat step 3 and 6 at different temperature. Repeat everything, you just start with different temperature. Okay, part 1. Identify the dependence variable. Dependence variable, it depends on the one that we change. In this experiment, we can change to any temperature. We can use 25, we can use 30, we can use 40, we can use 50. Once we change the temperature, then the absorbance will change. Absorbance depends on the formations of the products, which is the iron thiocyanate, means this one. Okay, it will form this. The absorbance depends on this product, and how much of these products produced at certain temperature is always different. So that's why when temperature change, the absorbance will change. So the dependence variable must be absorbance. Once the temperature change, absorbance will change. Part 2. Describe how you would adjust the temperature of water in the large pickle to obtain the temperatures of 10 degrees C. Just now is 25. If we want to reduce the temperature, so we just add ice into the pickle. This is the easiest one. Or you can use the thermal temperature control water bath to make it 10 degrees C. But this is a faster and more straightforward method. Part D. A student obtains the result given in table 2.2. Just follow the instruction here. Okay, part 1. Use the calibration graph in the figure 2.1 to complete this column 3. And make sure it's 1 decimal place. So now let's check the absorbance. At 25 degrees C, relative absorbance is 0.6. So from here, 0.6, we can get, okay, this one, 0.6, and another one is absorbance 0.42. So 0.42 is here. 0.42, we will get about 6.2 here, right? So just get this concentration of the iron thiocyanate from this calibration graph. Okay, so which is 8.9 and 6.2. Okay, after that, use this concentration. Again, remember is 8.9 and 6.2 times 10.85 mole per dm cube. After that, use this value in the equation 1. Substitute the values in equation 1 to get the constant. So the first one, you should get 107. Okay, just substitute the values, 8.9 times 10.85, okay, over this 0.001 minus 8.9 times 10.85. Okay, make sure it's square here. Okay, then you will get 107. Use the same calculation, you get 70 for the 55 degrees C. Okay, after that, part E. Another student does the same experiment for the 7 different temperature, something like this, right? So log K versus 1 over temperature. Okay, later we get back to these graphs. Okay, theory predicts the relations between the K1 and the T, the temperature, is given by equation 2, this equation. Okay, just now is log K1 versus 1 over temperature. So from this equation 2, we know that log K1, this is Y. Okay, 1 over T here, 1 over T. So this one is the X. Means negative delta H over 2.303 R. Okay, so this is a gradient. So later we use this one to get this enthalpy. Okay, part 1. Explain why the graph supports the relationship between the K1 and the temperatures given in equation 2. Okay, because from here we know that it's a straight line, see? Straight line. So, and this one is directly proportional or is proportional. Okay, the graph is a straight line, so means the log K, okay, it was proportional to this 1 over temperature. Okay, part 2. Circle the point on the graph in figure 2.2 that you consider to be the most abnormalous. It's quite obvious here. Just circle this one. At this temperature, the log K is supposed to be somewhere here. And this log K1 depends. Okay, let's get back to the equation. It depends on this X. X is the concentration of the product. So means at this temperature, the concentration of the products, which is the iron thiocyanate, is not really there. So why? Okay, there were no errors in the measurement in the experiment. Okay, means the meter is okay. A student correctly suggests that the abnormality was caused because the absorbance was lower than expected, like I told you just now. Suggest why the absorbance was lower than expected. So means again means the product is lesser. So it's caused by, okay, not all the solution B was transferred to the solution C. Means it's not exactly 5 cm cube added to solution C. That's why the products that produced is lesser than expected. Or you can say that the reactions not reach equilibrium. This one is still acceptable. Okay, part 3. Determines the gradient of the line of the best fit. State the coordinates of both points and use it in the calculation. Give the gradient in 3SF. For my coordinates, the coordinates I chose, they are these two. You can get your own coordinates. It's okay. Okay, make sure you calculate this accordingly. So just delta y over delta x. Okay, so use for mine. So I use 2.12 minus 1.78 over 0.00356 minus 0.0296. So is about 567 Kelvin. Okay, so you can use your own coordinates and do the calculation. Yeah. Okay, part 4. Use the gradient calculated in the part 3 and the equation 2 to calculate the values of enthalpy change. Okay, this is quite easy now. Gradient, just now I already told you, is this one, equal to negative delta H over 2.303 R. And again, the gradient is 567 from my calculation. So it's equal to this one now. Okay, so eventually we'll get delta H is negative 10851 joule per mole. Remember, this part after calculates, okay, we will get joule per mole first. Then we need to convert it to kilojoule, divide by 1000. Then we will get negative 10.851 kilojoule per mole. This is always the parts that you need to be careful when you use this kind of equation, right? Okay, so that's all. Thank you.